in general, there is no relationship between the velocity of the center of mass, like how fast the center of mass is moving, and also the angular velocity at which it's rotating. These two don't, there's no special relationship between them, right, in general. However, there is a very specific type of motion for which these two quantities are connected, and that is called rolling without slipping. So let me just quickly explain what rolling without slipping is. You're all familiar with it because I've talked about it a couple of times so far, and it's also something that you're quite used to. So you know very well from practical experience the difference between slipping, right, versus not slipping. So if you just imagine a car that's on a very slippery surface, then the wheels of the car will skid, right? That is rolling with slipping. But when the car is normally moving on an ordinary road, then the motion of the car is rolling, motion of the wheels is rolling without slipping, and both of these are quite familiar to you. So you know exactly you know very well the difference between rolling with slipping and rolling without slipping. But what I'm going to focus on now is just look at this a little more carefully. What's the difference between rolling without slipping and rolling with slipping? So we've talked about this before. If you just imagine this wheel, we've had the same discussion before, so it's not exactly new. So if you just imagine this wheel that's rolling without slipping, consider a point A and another point B and another point C over here. The point A is in touch with the ground right now. If it's rolling without slipping, the point in touch with the ground just for one instant will be at rest, right? So point A, just for that one instant, will be at rest, and the whole wheel will be pivoting around A just for one instant. The very next instant, the wheel will look like this. Just imagine A, B, and C are pretty close to each other. The very next instant, A will have moved up over here, B will be the one that's touching the ground, and C will be the one that's about to touch the ground next. And at that moment of time, B will be just momentarily at rest, right? And the whole wheel will be pivoting around B. So B will be the one that's momentarily at rest, right? And then the very next instant, the wheel will look like this. C will be the one that's in touch with the ground. B and A have moved on. So at that instant, C will be just at rest, just for that moment of time. A and B will be moving, but C will be at rest just for that moment of time. And so that is rolling without slipping. The point of the wheel or ball or whatever round object that's in touch with the ground is momentarily at rest, right? So that is rolling without slipping. And rolling with slipping would be something like this. The wheel, you have A, B, and C. Let's say it's a very slippery road. And let's say it's so slippery that the wheel is just sliding along. So it's moved from here to here, but A is still on the ground. And B is here and C is here. So it's hardly rotated at all. It's just sliding along. So the point A is moving against the ground, right? It's not at rest. It's moving relative to the ground. The point in contact with the ground is moving relative to the ground. That is rolling with slipping. And rolling without slipping is when the point that's in touch with the ground momentarily is at rest, just for that one instant. It's at rest. And then the very next instant, another point is in touch with the ground. Is that clear to all of you? So the important difference is over here, you have static friction. And over here, you have kinetic friction because the point in touch with the ground is sliding against the ground. So you have kinetic friction over here. This is a very important concept. So let me know if it's not clear. If anything is not clear, I'll be happy to explain it. Yeah, go ahead.
I understand the rolling with or without slipping,
Yeah.
but can you go over like the first point on the slide where you said there's no relationship between omega and VCM for an
Yeah. So for example, suppose let's take the rolling with slipping case, right? When it's slipping, and let's say that it's rotating. So maybe it is slowly rotating with angular velocity omega, and the speed at which the center of this is moving is VCM, right? So if it is slipping, then there is no relationship, no particular relationship between omega and VCM. So if you know, if I tell you that this is moving with a speed of 2 meters per second, it's sliding across the ice with a speed of 2 meters per second, that's the VCM. Can you tell me what the omega is? You would not know. I mean, it could be rolling really fast while it's sliding along the ice, or it could be rolling really slowly while it's sliding along the ice, or it could not be rolling at all. It could just be sliding along the ice if it's really frictionless. So there is no relationship between the rate at which it's spinning and the rate at which it's sliding along. That makes sense? That's usually the case. Like if you just take a ball and throw it in the air, you will see that as the ball flies through the air, it might be spinning, and it also has some kind of it also has its forward velocity, the velocity of center of mass, and the rate at which it's spinning has really no relationship with the velocity at which it's moving. That's usually the case, but we will see in a moment that when it's rolling without slipping, the velocity at which the center of mass is moving, VCM, and the rate, the angular velocity with which it's rotating, we will see just now these two quantities are connected. That makes sense?
Yes.
Yeah, but in general, there is no connection between the rate at which something is spinning and the rate at which it's moving along. All right, so that very good question. That brings us to our next point. Yeah, when an object is rolling without slipping, then omega and VCM are connected. And let me just ask you a very quick question. If you look at this picture at the bottom over here, would you say that the wheels of the car are rolling with or without slipping right now? Looking at this picture, what do you think?
Without slipping.
Are you sure? Think about that a little bit more. Anybody else? I mean, now you can guess what the answer is, but can anybody tell me why it would be, how we would know that this is actually slipping, the wheels are actually slipping?
With slipping because it's disturbing the ground so much.
Absolutely, absolutely. So the fact that it's kicking up so much dirt is telling us that the wheels must be moving against the ground, right? But when it's rolling without slipping, the point of the wheel in touch with the ground is not moving. But in this case, it's rolling and slipping. So that slipping or sliding against the ground is what's kicking up all the dust. That makes sense? Ali, is that clear?
Yes.
Yeah. So just, I mean, if I had just shown you a picture of a car, you would not necessarily know whether it's rolling with or without slipping. But in this case, we can tell because there's so much dust being kicked up. That can only happen if the wheel is sliding against the ground and kicking up the dust, right? So that's why we know in this case that it's rolling with slipping. All right. Now,
I have a question.
Yeah, go ahead. Yeah.
So the video we saw earlier about the rover kicking up dust on the moon.
Yeah.
Was that also slipping then?
Yeah, there would be some amount of, there would have to be some amount of slipping if it's kicking up the dust. Very good point. Yeah, generally when you have rolling without slipping, when you get a very good grip on the road, that's when the rolling without slipping happens. But on the moon, the surface of the moon is so dusty that the wheels of the rover were not getting a very good grip, and so that's why you were having some slipping against the ground. That makes sense?
Yeah,
all right,
thank you.
sure. Okay, so now let's look at the relationship between two variables when an object is rolling without slipping. So you have rolling without slipping right now. So just imagine this this disc or this tire or something that's moving along the road, that's rolling along the road without slipping. The center of mass is moving with velocity VCM. And the wheel is rotating. This is a circular wheel. So you have to use your imagination and think of this as circular. The wheel is rotating with angular velocity omega. You all know what omega is. Omega is delta theta over delta t, or d theta dt, whatever is the rate at which the angle that it's making is changing. So it tells you how fast it's rotating. So you have this wheel that's rolling without slipping. Let's say that right now, and let's say the radius of the wheel is r. All right, let's say that right now the point in touch with the ground is A. right? That's the name of the point of the wheel that's in touch with the ground. Okay, so we are going to try to find a relationship between these two variables, VCM, which tells us how fast the center of the wheel is moving, and omega, which tells us how fast the wheel is rotating. We'll try to derive a relationship between these two. All right, now, right now the point A is in touch with the ground. We'll let this roll. And so as this rolls to the right, the point A will go up, right? So maybe a moment later, the same wheel will look like this. The point A has moved up over here right now. And so the wheel has rotated some. We're going to wait until the point A comes all the way back down again. So all these are the same wheel. So we just let it rotate, roll a little bit longer until the point A is back on the ground. So the point A just went all the way around until it came back down to the ground, right? So my first question is this: what distance has the wheel traced out? What is the distance the wheel has traveled while the point A went from being on the ground to all the way up and then back to the ground? What distance do you think the wheel has traveled? Radius of the wheel is r.
To R pi.
Did you mean the circumference of the wheel?
Yeah.
Yes, 2 pi r, exactly. So let's be really clear about that. How do we know that the wheel has traveled a distance 2 pi r? That is simply because it's rolling without slipping. So every point on the wheel gets one opportunity to touch the ground, right? And no point can slide against the ground. So every point on the wheel just touches the ground once, and then it's the next point that touches the ground. So every point on the circumference must have touched the ground, right? Once. And so the distance traveled on the ground is equal to the circumference. Is everybody clear about that logic? If the wheel was slipping, then we had no way of knowing how much distance it's traveled, because the point A might have been in touch with the ground for a while, and then the wheel rotates a little bit and the next point comes in touch with the ground and stays in contact for a while. But that's not what's happening here. The wheel is rolling without slipping, so every point on the wheel just touches the ground exactly once, and so the distance traveled by the wheel is 2 pi r, right? All right, from this distance, we can figure out, let's say that it took a time t to cover this distance, right? So that means time t is the time period of its rotation, because in time t, the point A went from being on the ground, going all the way down and coming back down on the ground. So time t would be the total time for one full rotation, right? So this velocity of the center of mass of the wheel is distance traveled by the wheel divided by the time it took to cover that distance, 2 pi r divided by t, right? That's the velocity of the center of mass of the wheel. Now, you might recall this formula from chapter 3. This quantity 2 pi divided by capital T, what is that quantity? 2 pi is when it's doing a full revolution, it's covering an angle of 2 pi. It's rotating through an angle of 2 pi, right? And the amount of time it takes to rotate through that angle is t. So the rate of change of angular position is just angular velocity, right? And so this 2 pi over t is nothing but omega. So we get this formula, VCM equals r omega. This is a very, very important relationship. VCM equals r omega. This is only true for objects that are rolling without slipping. All right. Now, a very common mistake that students make is that they confuse this formula with another one that you've seen in chapter 9, which is the tangential velocity is equal to r omega. Now, these two are connected. In fact, you can use this. I gave you a very simple proof of VCM equals r omega, but there are other ways of proving that too. And in fact, you can use V tangential equals r omega to prove that. But it's very important to realize that these two formulas are very different. V tangential equals r omega is talking about the velocity, the tangential velocity of something that's going around in a circle, right? So if you have an object that's going around in this circular path, V tangential would be this velocity. So that's what this formula is talking about from chapter 9. But in the formula that we just learned, VCM equals R omega. VCM is the velocity at which the center of the wheel is moving, right? So that's VCM. And when it's rolling without slipping, it happens to be equal to R multiplied by omega. So these two formulas look similar, but the V's are completely different. So they're completely different. They apply in completely different contexts.